So we are starting now. Okay, so in this lecture, we will start free body diagram. Sometimes in short, it is regarded as FBD. Free body diagram, and it is regarded for FBD. FBD means nothing to maintain the body in equilibrium, that is in rest or in the motion. Actually, in the rest, we will discuss statics, that is bodies are in rest. So here, to maintain the equilibrium, there are a number of forces will act. Now, so there will be a support. So in free body diagram, what we do, we have to remove the support. So in free body diagram, we have to remove the support and then have to draw the diagram. So free means the body will have to be freed from any support. Then we have to draw the free body diagram of it. So I'm giving the example now. So here, so all the body will have to be considered here will be of rigid body. That means the relative distance between the particles will remain always the same irrespective of the applied forces. The relative distance between the particle of the body will remain the same. In the engineering graphics also we learn the concept that these lines are called hatch lines. The hatch line has got different uses, but here the hatch line is used to show the fixed surface. So it is so as the horizontal, as I have drawn a horizontal surface and given hatch lines, so it will show the fixed horizontal surface. The hatch line here represents the horizontal fixed surface. Now here I have taken a rigid body and it is a point contact. Although in practical cases, this is you can take a wheel is sliding over a road or wheel is fixed over a road. But in practical cases we know that the point contact cannot be made every time. But here, ideally, when to draw a free body diagram, we consider that here a point contact will be made. Okay, so that roller will make a point contact with the road. Now, at the second step, to draw the free body diagram of the ball, we need to draw the ball again, ball of same size, and it will have to be removed from the support, that is the floor. So the support has been removed. Now, for that support, we know the body is creating a force on the floor, and the floor will create a reactive force on the body. The concept of the free body that we need to draw, we don't need to draw the active force. We need to draw only the reactive force given by the floor on the body. So here, the reactive force will be vertically upwards, isn't it? If I take that surface as A or point of contact as A, then the reactive force will be RA or reactive force at point A, and always the body will have got some weight. So that weight force will always be vertically downward force. So that will have to be shown. Now, by giving vector, we know that the weight is being drawn like that, but from the vector concept we can draw weight like this also. But this RA, as the reaction is created at point A, so we have to draw the force at A only. We cannot draw the force like that. Following the vector concept, we cannot draw the force like that. So this diagram is wrong. So we have to show RA at A point only. And by following the vector concept, I can draw weight here. So this diagram is right, but this is not right. Okay. Now, if I take another example, now let us consider a vertical wall. Okay. So here a vertical wall is shown. Now let us consider a ball again. Now the ball cannot remain in the vertical wall like that, so that there has to be one support also, or a string also, so that the ball will remain in that position. The string will be added. Let us consider this point as A, but the string is being attached, and this point of contact between ball and the vertical wall is B. So now, to draw the free body diagram of it, we need to draw again the ball, isn't it? So now, a tensile force will act, and the force of tension will always be towards the support. Please remember this. The tensile force will always be towards the support, and in this case it will be towards B, and for at point B there will be a reactive force RB. So this will have to be drawn also, and the weight, now the weight can be drawn vertically downwards, downward from O. If I consider this point O, then the weight force can be drawn like that. But if we draw this diagram like this, the angle of TA will remain the same. So make this with the direction TA. RB. But if you draw weight like that, it is also correct, because the position of TA and RB remains the same. That is our main objective. So weight force can be shown like that and like that also. But it is better that if you draw the diagram like the first one, then the forces can be understood very easily. Three forces. Here you need to draw the force from away the, and again at the next step to make our calculation, RB can be drawn. If I want to draw all the forces away from the center, then I can draw RB like that. TA is already away from the center, and weight force is like that. So hence you can calculate the things easily. Weight of air, just weight of the body. Okay. The diagram can be like that. So these are the ways to draw the free body diagram, different ways to draw the free body diagram. Now, the third diagram, I will take a ladder. Okay. So I will consider vertical wall. Also, I will consider horizontal force simultaneously. As in the first diagram, I have considered only floor, and at second diagram, I have considered only wall. Now I have considered the wall and the floor also. Now I will consider a ladder in this case. Okay. Ladder AB. Now please remember one thing, that all the free body diagrams here will have to be drawn taking the point of contact as smooth. The point of contact as smooth means there will be no frictional force act. Okay, so we always omit the frictional force. So when we will study the chapter friction, we will consider the frictional force. But here in the free body diagram, here in this chapter, for equilibrium of the bodies, we will consider for the time being the point of contacts are smooth, so that the friction will not be there. But practically it is not the case. You know that the practically friction is always present. But here ideally we will take, for the time being, we will take the surfaces as smooth. It will be mentioned in the problem that whether you have to take the surface smooth or frictional force will have to be considered. So here we are taking only that the surfaces are smooth, so we don't have any friction. And the weight of the ladder will be given, has been given as, let us say, WL. It will be always act from the middle of AB. like that. The weight will act vertically downwards. Now, to draw the free body diagram, we need to draw AB again separately. A, B. Okay. Now, at the middle, there will be the weight of the ladder, the WL. Now, for point A, we'll have a reactive force like that, isn't it? So that reactive force will be RA. And at point B, we have a reactive force vertically upwards, like that. So that force will be RB. So that's how the free body diagram of the ladder can be drawn. So these are actually some examples. Now, okay, so I will erase these drawings and we'll create a new page. The second page is available here. Now, let us consider a pulley system here. There's a pulley is being hung on the wall, and we have a load here. Also loading hung from here also. And the floor is here. Let us say this weight is 800 Newton and this weight is 600 Newton. If I want to draw a free body diagram for the 800 Newton or 600 Newton also can be drawn. So we have tension and we have a, let us say this point A, we will have RA and the weight will always be there. So here we cannot show the weight, so or I can show RA minus WA because weight will be at the opposite direction. In this manner, this can be shown also. Okay. Or to avoid confusion, I can write 600 Newton here or 800, whatever the weight may be. 800. So that will indicate that this is of weight 800 Newton. So separately, we don't have to draw the direction because it is well known that the direction of weight will always be vertically downward direction. So these are some free body diagrams. I will give you example of some more diagrams also with some more diagrams also. Okay, let me erase that first. Yeah. Okay. I'm giving more of I'm drawing more free body diagram. Let us say inclined plane. A fixed inclined plane. Angle will be given. Let us say the angle is 60 or whatever alpha. Okay. Now the body is there. Okay. And to keep it in equilibrium, a horizontal force, let us say F, is there. Unless the F force is there, the body will come down from the floor, come down high from the inclined plane. Okay. Now, to draw the free body diagram of this body, we need to separate that body from the support. Then we need to draw the F force, because F force is already there, and there will be a weight of the body. Let us say it is W, P, the weight of the body, and for the inclined plane, we have a reaction force. Let us it is RA. So by calculating the angles, we can easily find this inclination of RA if that angle is given. We'll discuss them in detail, so we will solve the numericals. For the time being, just I am showing the directions of the force or the reactive forces. Now, I am giving another example. Let us say the rigid body is there and two inclined planes are there at different angles. You will touch the plane always. Okay. The two inclined planes are given and a rigid body is there. Let us say the angles are given also. It is 60 degree. It is, let us say, 45 degree. Whatever that angle might be, and this is, say, this point is A, point of contact, and here the point of contact is B. So now, to draw the free body diagram of that body, the body has to be separated from the reactive, from the supports. Then there will be, let us say, RA, and another reactive force will be there. Let us say RB. And the weight of the body will always be there. It is W. So that's how now that angles can be calculated easily if the angles are given. And if we extend the thing, then with vertical also this angle will be 60 degree. And if we extend the thing with vertical, this angle will be 45 degree. Hence that force analysis can be made. This can be split up into horizontal and vertical components. Then by means of equilibrium, we can solve the numericals. So hence this is the basic idea of the free body diagram. That is how the free body diagram is being drawn. And now in this class we will learn also a theorem, Lami's theorem. So that can be solved by creating or analyzing the vertical and horizontal components of forces. And another way to solve this problem is by applying the Lami's theorem. Now, what is Lami's theorem? I am telling. So there are two ways to solve the numericals. The first way, you can split up the forces into vertical and horizontal components, and by creating equilibrium, that is summation of vertical forces 0 and summation of horizontal forces 0. By making that, you can easily solve the problem. And there is another way also by applying Lemmy's theorem. Lemmy's theorem, LEGOREM. Another way is the Lemmy's theorem. So in Lemmy's theorem, this Lemmy's theorem can only be applied if the number of forces are 3. Okay. The Lemmy's theorem cannot be applied if the number of forces have become more than 3. But it can be applied only when the number of forces are 3. So let us say body is under equilibrium by means of 3 number of forces, and this force is F1, and angle, this angle is alpha. This force, let us say F2, this angle beta. I consider this force as F3 and consider that remaining angle as gamma. Then the Lemmy's theorem says that so the body is under equilibrium, so body is in equilibrium under the action of the 3 forces. Then Lemmy's theorem is saying that each force is proportional to the sine of angle between the other 2 forces. Okay, so each force will be proportional to sine of angle between the other forces. So each force is directly proportional to sine of angle between the other forces, like that. So F1, so then F2 sine beta, sine of angle between other forces, as F1 is proportional to sine of angle between F2 and F3. F3 is proportional to sine of angle between F1 and F3, and F3 is proportional to sine of angle between F1 and F2. So gamma. Now if we make proportionality constant as same, so if F1 by sine alpha equals to a constant, F2 by sine alpha equals to a constant, and F3 by sine alpha will be equals to a constant. And if the value of constant is same, then we can write, combining the equations, we can write F1 by sine alpha equals to F2 by sine beta equals to F3 by sine gamma. So following both the ways, this system of forces can be analyzed. One is by analyzing the splitting up the vertical and horizontal components, and by making summation of horizontal forces 0 and vertical forces 0. And other way to solve the equilibrium problems is through the Lemmy's theorem. And Lemmy's theorem is stating that if a body, let us say body here O, I have taken the body as a particle O. If a body is in equilibrium under the action of 3 forces, so here the Lemmy's theorem can only be applied if our number of forces are 3. If the forces have become more than 3, then you cannot apply the Lemmy's theorem. You have to analyze the vertical and horizontal components of the forces then. So then Lemmy's theorem is saying that each force is proportional to sine of angle between the other 2 forces. F1 is proportional to sine alpha, F2 sine beta, F3 sine gamma, and if the value of proportional constant are same for both the three cases, then we can write from Lemmy's theorem F1 by sine alpha equals to F2 by sine beta equals to F3 by sine gamma.